Hey, good morning, guys. This is Miss Johnson. This is, and I didn't write it because here we are. This is the Unit 2 introduction video. It's not associated with any work. It's going to be kind of high-level philosophical stuff. So if you don't understand what's going on, perfect. I just want you to hear these words and see some pictures before we jump in to assignments and to lessons and to other videos. So yeah, the big three things that we're going to be talking about this unit are continuity, so when a function is considered continuous and when it's considered discontinuous. We're going to be talking about limits. We're going to be able to find them graphically and algebraically, so like writing things out math-wise and seeing pictures. And then we're also going to be talking about something called the derivative, and I didn't write that, but here we are, derivative. And this is the word I kept saying, this is the word I kept saying meant the slope. When we found the slope of different graphs, or when we found the slope equation of different graphs, we use the derivative. So those are the main three things we're going to be hitting on this unit. I have a little introduction written up, so I want to read it. The big ideas and skills of Unit 2, limits and derivatives, are continuity and discontinuity, nice. Computing limits algebraically and graphically, nice. Computing slopes for tangent lines, and that involves derivatives, we're thinking about derivatives, and computing derivatives with the definition and with the power rule. Let me talk about continuity for a second. Then I'll talk about limits. And then I'll talk about derivatives. Y'all know how this is going to go. Okay, for continuous, we've always been given the definition that if you can start at one endpoint and then draw the entire function without picking up your pen, that's a continuous function. And that's true, but it doesn't seem like a super mathematical definition, and we're going to make it super mathematical, right? We're going to have an airtight definition for what a function means to be continuous. So discontinuity, we're also going to have three examples of what it looks like graphically and what functions are doing when this graphical thing happens, right? One thing that would make you pick up your pencil when you're drawing a function is if the function like went off to infinity and then we had to pick it back up down here, right? And this is called an asymptote. Nope. Right? Another problem that a function has when you're doing continuous stuff is you're drawing, and then you get to a hole. And honestly, it doesn't matter if that hole is filled in the top or if this function simply does not exist there, right? Those are both holes, and they both make you pick up your pencil to continue. And then the third kind is when a function jumps. The jump mainly happens if you have a piecewise function, like when we had the speeding ticket assignment, right? The asymptote and the hole happen with rational functions. When we've got a polynomial on top of a fraction and a polynomial on the bottom of a fraction, this leads to a lot of asymptotes and a lot of holes, and we'll explore that. Okay, the next big idea of calculus is a limit, and this is, I say big idea, I'm underselling it. This is like the bedrock of all of calculus. So a limit is how we describe, if I wanted to say, okay, this function does not exist, this is f of x, this function does not exist at x equals 10, right? If you plug in x equals 9, you'll get something around 5. If you plug in x equals 10, you'll say that it does not exist, right? Because there's a hole. Mathematicians, and we, being mathematicians, will want to be able to say, okay, what happens when x gets kind of close to 10, right? Where is f of x going when x is getting closer to 10, comma, we do not care what actually happens at 10, right? So mathematicians are interested in saying, as we plug in numbers that get closer and closer to 10, which numbers are we getting out? We're getting out numbers that are approaching 5. And this happens from both sides. If we're getting closer and closer to 10, these numbers are getting closer to 5. And we're going to want to be able to formalize closer to. We're going to be able to want to formalize, like approaching, because a lot of things in calculus are like, what happens when these things get infinitely small? or what happens when these things become infinitely many in count. And we want a way to talk about that mathematically, both graphically and algebraically, as is the case with most things. And then, yeah, limits they're the bedrock, right? Because when we come down to derivatives, we're going to see something get infinitely close, and then we're going to say, that's where you use a limit. So a lot of times we're interested going to derivatives. Section break, next section. Going to derivatives, the impetus for wanting to learn how to do this is if we've got a function that's not a straight line, I want to be able to reasonably talk about its slope, its steepness at any point, right? I want to be able to say, here's a point on the graph. How fast am I moving right here? How fast is the function growing? What's the slope of my tangent line is how we usually think about this. A tangent line is a line that just touches the line once. This linear line has a slope. It's just rise up or run. And drawing the tangent line, we can eyeball it graphically, but we want to be able to say, at this point in the graph, what's the exact tangent line? What's the exact slope of this line, right? What's the exact slope of this line? And the way we're going to do that is through a derivative. We're going to be able to see, a function is, say, this function. We're going to have a not so magic process, right? We're going to have a process to find its slope equation, which is an equation that if you plug in the number you want to find, you plug in -1, you plug in 3, you plug in 20, right? Whatever, it'll just spit out the slope instead of spitting out the y value, right? So, for instance, if this was f of x, it's not, but let's pretend, I would plug in 20 to the original equation to figure out the y, as we've been doing since Algebra 1, right? And I would plug in 20 to the slope equation to figure out the slope of this tangent line. And that seems like a magically acquired equation, but actually it's pretty chill. The reason we have limits coming to this, in order to develop this process, this not so magical, but feels kind of magical derivative, what we do is we're just going to take 2 points that are close to this one we want. Oh, this shouldn't be in. Let's make it black. The way we know how to compute slope right now is take 2 points, do this y2 minus y sub 1, x2 minus x sub 1, and then find the slope between them, right? And that's as if we had taken 2 points, drawn a straight line, this straight line, and found this straight line slope. And you might say, okay, well, that's not even close to this slope, right? This one's negative and this one's positive. And I'd say, you're right. So let's take a closer point, right? Let's say, okay, maybe picking 20 and 10 was a bad idea. Let's pick 20 and 15. Okay, you take those slopes. That line's a little closer to this one, right? It's flattening out. Say we took 20 and 18. That's getting better, Say we found the slope between, if we want the slope at 20, right? The best point would be either 19.99999999999 kind of thing, or 20.0000000000001, right? We want the closest point to either side of this target point to be able to calculate the slope, except we'll eventually use limits and we'll say, what happens as it gets closer to just being itself, being the actual tangent, right? And then we'll use limits to compute where these slopes are getting closer to, and then we'll be able to figure out the slope of the actual tangent line. And then the last thing we'll learn is something called the power rule. It's something where we don't have to use limits. It's kind of a shortcut. So we'll learn a theorem that whenever we're working with polynomials, we can quickly figure out the slope equation without having to think about limits every time. And that usually feels like a magic trick that students are like, why didn't you tell me that at first? But I'm pretty interested in everyone understanding kind of what a derivative actually is. But then, yeah, a lot of this class is going to be learning theorems that feel like tricks to compute derivatives and integrals. and limits, actually. So get ready, get pumped. All right, guys, as a breakdown of what's going to happen on Tuesday's class, and Tuesday is October 13th. Oh, good day. October 13th, Tuesday, our next class. The breakdown is going to be, we're going to have a class meeting. We're going to have a class meeting where we talk about stuff like how the group sizes work. Did you like document versus Quib submissions? Testimonials about office hours for people who actually went. Social subgroups that people have talked to me about forming that aren't just like official clubs. How you want me to put assignments on Schoology. I've got a whole list of stuff I want to hit on the class meeting. And then anything you guys want to bring to class meeting about how the class is going, how school is going, what I can do to help there, and what you can do to help each other. It's totally, the whole hour is going to be class meeting. It's definitely still required. Please come. And then the afternoon, I will make a more focused video and have an assignment, and then we'll hit the ground running with limits and derivatives. All right, guys, have a good weekend. Have a good long weekend. And email me if you have any questions ever. Thanks.